So, moving on. So, going back to our class, as a starting point, let me go back to, I'll go, as I was saying in the beginning, today I will show you some examples of epidemiological surveillance, and I will start with the need of nowcasting models. And as I mentioned in our first class, we discussed a little bit about the time flow of, specifically of information flow, in terms of information flow, whenever we have a case being detected of whatever disease that we want to monitor, right? So usually we have a time difference that might vary between whenever the case actually started or happened and when the information associated with that particular event, so the notification of that particular event, is inserted into an official database, so become visible and actionable by any surveillance system or team, right? And so here, this is just an example of one way to looking at this, the impact of that process. Again, in the case of SARI in Brazil, so severe acute respiratory infections, what we have here is just a subset of states, Brazilian states. For each of those plots, the vertical axis, the y-axis, is the number of weeks between case onset and date of database insertion associated with all the cases that happen at any particular week. Okay, so the x-axis is weeks of symptoms onset. So for every week, all the cases that have been notified for that particular week, the lines show how long it took in terms of epidemiological weeks for us to have in the database 80% of all the cases, the black line. The yellow or golden line is how many weeks we have to wait to reach 90% of all the cases that happen at that particular week. And in blue, how long it took to reach 95% of all the cases that have been notified at any particular week, okay? So you can see that not only we have heterogeneity in space, right? Because each of those states have a different pattern. You can see, for instance, for São Paulo, after 2 weeks, we already have usually at least 80% of the cases already being inserted. If we're looking at least 90%, still after 3 weeks, we already have that much. And after 4 to 5 weeks, we already have 95% of all the cases that happen at a given time already inserted into the database. But I remind you that 4 weeks is already 1 month, right? Now, if we look at the neighboring state of Rio de Janeiro, which is also an extremely wealthy state in Brazil and extremely developed state in Brazil, the situation is already completely different. For us to have 90% of the cases, we already have to wait from 5 to 6 weeks, right? And to reach 95% of the cases, we're talking about 10 weeks. So more than 2 months to have at least 95% of all the cases that happen at any given week being notified, inserted already into the database, okay? And you can see also that for some states like Santa Catarina, at least in terms of 90%, 95%, Espírito Santo, Bahia, Goiás, and the federal district there, you can see that also over time we might have variation in how long it takes for cases to be inserted into the database. So this is an example of why, if we want to apply any method to deal with this aspect, usually you should stratify your cases as much as possible in space, at least, and also, if possible, have your model being updated weekly or at least at a certain frequency to take into account variations that also happen over time, not only over space itself, okay? Because the same method calibrated for one state will likely not be good enough for another state because the pattern is different, okay? And the same parameters that we extract from our model at a particular time might not work well the next month or sometime later, because we are even at the same place, the pattern might change over time, okay? Now, the diagonal there, the dashed diagonal that you see over there is what we call the event horizon, more or less, right? Because since we are looking at any given week, how long it took for cases to be inserted into the database, if we are looking at the pattern for last week, we only have last week and this week of database insertion. So at most, cases so far would have been inserted into the database after 1 week only. So this is just to clarify that in the most recent weeks, the delay is short, not because information is being inserted quite well, but because we didn't have time yet to observe all the information, okay, associated with what already happened, okay? Of course, we can present this data in different ways. For instance, this is 2 other examples of the same process. So on the left-hand side, again, SARI cases in Brazil from 2020 all the way to week 32 of 2021. The solid line over there is the number of weekly cases aggregated by symptoms onset with and the data being extracted by the end of week 33, 2021. So if you go back, if you're looking at previous weeks, especially in terms of 2020, so from 1 to the first block here, from 1 to 52, data is, you can consider that this data is already consolidated, right? That everything that happened already have been inserted into the database. So this, we might think of what actually happened, okay? So the ground truth. Now, the colored dotted lines, on the other hand, is this exact same information, but only what we had in the database by the end of weeks 16, 20, 24, and so on and so forth. So the last point in any of those colored dotted lines is the last week of database insertion. Okay, so it's a snapshot of the same database at different points in time. And you can see that what we had was completely different to what was going on, right? Just by comparing the colored dotted lines with the solid black line, okay? So not only we are losing in terms of volume of cases, but even worse than that, the trend is completely lost because it's always going out, right? Just because of the information flow, not due to the epidemiological situation, okay? Now, what some surveillance teams do to try to accommodate for that fact is, well, instead of looking at the same data in terms of symptoms onset, let us aggregate the data by database insertion, okay? Well, could be a good idea. And the black dashed line is exactly that effort, okay? With the data extracted at, by the end of week 33, 2021. And you can see that still there's a lot of difference to what was going on. We not only have a time shift, which is associated specifically with the delay in this process. So we have more or less, this is the aggregation for the whole country. So we have about 2 to 3 weeks as a time shift between the two curves, right? So again, we are losing the trend. We are seeing what happened 2 weeks before. But also, and not only so we are losing when things are starting to get worse, but we are also losing when things are starting to get better, right? And if you see, for instance, between weeks 17, more or less, to week 28, where we had kind of a plateau in our country in terms of what was really going on, by aggregating the data by database insertion, we will think that the cases were still going up, right? And this has impacts on what you should do on the field. And of course, the worse the delay, the worse it will be the comparison between the solid line and the dashed line, not only against the dotted line, okay? So this is why, in general, unless the surveillance system at place is extremely efficient in uploading the information to the database, let's say most of the cases takes only 1 to 2 weeks, then if that's the case, then aggregating by database insertion should be fine. But that's usually not the case, okay? And on the right-hand side, we have another way of looking at the same process. And this is data from dengue surveillance and suspect dengue cases. And each of the dotted lines, so the solid line is, again, number of new cases per week after we have waited long enough for the data to be inserted into the database, so it's the ground truth, let's say. And each of those dotted lines is the same information when the week ended, the last week ended, 1 week, the same information 1 week later, 2 weeks, 1 month, 2 months. And you can see that in terms of dengue, this is for Rio de Janeiro, if I'm not mistaken, in 2013. You can see that even 1 month later, we were still quite far from what was happening, and the trend was still pointing downward. After 1 month already, see? Okay, so this is why one must look into a way to deal with that process if you want to have a system, a surveillance system that is useful for weekly situation reports, right? So on-time situation reports. Otherwise, the picture that you're looking at might be completely different to what is really going on, okay? Of course, there are other systems that might be faster in the process, and then you don't have to worry about. But first of all, the idea is that, first of all, try to have a way to look into this process to see what is the impact of the information flow, to see whether you need to come up with any system any way to deal with it or not, okay? So what is the information that is fundamental for us to be able to analyze this process? I must have in my notification system at least date of onset, right? Or the event date, whatever it may be it symptoms onset, be it hospitalization date, whatever I need or I want as the reference date for what is happening, for what I want to analyze, and also a variable that registers when the notification actually happened into the database. Not when a paper sheet was filled out at the healthcare facility, but when the information actually entered into the database, okay? You must have those two informations. Otherwise, to have this picture, this snapshot, we would have to come up with a system, for instance, that every week we take a snapshot of the database and we compare what we had last week to what we have now and look at the difference in terms of number of new cases for the same previous weeks, okay? So it's a way to go the other way around. So if I don't have those variables in my system already, a way to try to I lost the term. To infer this difference in time between event date and data uploading, okay? Is that clear so far? Good enough? Now, also, remember that for syndromic surveillance, we are not only interested, usually, in the overall cases, syndromic cases, but usually we also want to look at the data extractified by lab result, right? So for instance, for study surveillance, we want to know whether those cases were influenza cases, COVID-19 cases, RSV cases, and so on and so forth. For dengue surveillance, we have more or less the same thing. We want to know whether it's actually dengue, if it's chikungunya, or if it's something else, right? And then we have another time process going on, which is not only the case notification, it's still at the level of suspect cases, right? But also we have then a process that is going on in parallel that is testing, getting the result of the test, and again, the result of those tests being filled out to update the notification already in the system. And again, the date when the result comes out and the date when this result is uploaded into the database are usually not the same as well, okay? And for our system, at least for those two information systems associated with SARI notification and dengue, Zika, and chikungunya notification, we do not have a variable that allows us to know when the lab result was updated into the system. We know when the notification was inserted into the database, but in terms of lab result, we don't. So we can do something about this process, but not about the delay in terms of lab result. So for that, we just look at aggregated data over time to try to infer of those new cases, more or less, how many are associated with any of the different viruses that might be of interest for that particular surveillance, okay? Of course, there will be a margin of error over there as well, because what happened in the last 4 weeks might not necessarily be an accurate description of what happened last week in particular, okay? But it is what it is. So, how do we, one way to tackle this issue is, well, I can reconstruct this information or aggregate this information by building a matrix where I have for each line or each row of my matrix represents the date of event, and each column represents how many weeks it took, or days, or whatever time scale that I want to use as reference for cases of that particular week, for that particular row, to be uploaded into the database. So let's say for week number 3, N30, so the cell on my matrix associated with the third row, column 0, it will be the number of cases that happened at week 3 and that was uploaded at the same week. Column 1, it's the same thing, but cases associated with week 3 that were only uploaded 1 week later, then 2 weeks later, 3 weeks later, so on and so on. Okay? So if I sum over the row, I have the total number of cases that happen at a particular week. Okay? Because each week is how many time it took for those cases to be reported. Okay? So if I sum over all the columns, I'm summing over all the possible delays. Right? Any questions about this, the idea behind the construction of this matrix, the process? Is that clear? Okay. So what happens is when I'm getting closer and closer to the current time, this matrix will have cells without any information. Why? Because it didn't have enough time for the information to be inserted. It's the same idea of that diagonal that we had in the previous slide, right? So for instance, if I'm looking at last week, so thinking about time t, for instance, week t, I only have information about cases that happened at week t and that were already uploaded last week. So cases of last week that happened last week and were inserted into the database last week. Cases that took 1 week to be inserted, I have to wait for this week to end to have that information, right? So the cell associated with NT1, so what happened last week and took 1 week to be uploaded, this didn't happen already. So this is a blank cell on my matrix. And we have then a whole triangle of that matrix that is associated with that process. Why? Because for last week, we delay 1, 2, 3, and so on and so forth. There's no information. For 2 weeks ago, I have with 0 delay, with 1 week delay, but from 2 weeks delay onwards, I don't have any more. Right? It's the same logic. So this is why that we have that gray triangle there, which is what we're missing related to what already happened. Okay? Now, the red rows is the future already, in terms not only of information flow, but actually in what happened, right? Because this is what will happen in the following weeks. So, estimating the gray triangle is what we call nowcasting, because we are doing a projection about what already happened but hadn't, as of yet, been informed. The red rows is forecasting then, because it's a projection of what will happen in terms of the epidemiological scenario itself. It's not only a matter of information flow, it's a matter of actually predicting what will happen in the future at the epidemiological level, right? So gray area is predictions in terms of information flow only, and red rows is projections for the epidemiological process as well, Okay, so this is the main difference between nowcasting and forecasting in terms of this particular matrix. So, but in terms of statistical method, so what we need, what is the information that we want? Is the sum of our rows, so right? Because it's the number of cases that actually happen at any given week. So the process now is, in fact, is trying to come up with a way to estimate each of those cells. If I might be able to estimate what are the values for all of those cells that are missing, I have an estimation of what really happened, right? Because then I just sum over rows, and that's it, okay? So one way to tackle that, so we took advantage of a model that was developed for actuary sciences to predict what is the future cost associated with events, insurance events that already happened but wasn't already still informed, right? It's more or less the same idea. So we just adapted that model, and this is a paper where we describe the process itself. So each of those cells I will call little n index T and D, where T is the week of event, D is the delay. Okay, so NTD is the number of cases that happened at week T, but were only reported D weeks after. Okay? Now, I'm describing the process here in terms of weeks, but again, I could do the same process in terms of days, in terms of months, in terms of years, whatever. The logic is exactly the same. The quality of the estimation might vary, okay? But the construction is the same. So, and then what I will do is that we propose that those entries, NTD, they follow a negative binomial distribution. Why a negative binomial? To accommodate for over-dispersion that might happen, right? And we want to, with a rate lambda, and lambda then is what we will try to estimate, and we say that we assume that the rate of the associated with the negative binomial, the logarithm of that rate is a random process that has a mean mu, but also depends on an alpha parameter, which is a random variable associated with week of event. So alpha depends on t, and beta is a parameter associated with the delay. Okay, so alpha will take into account how the epidemiological process situation is varying over time, and beta will take into account how the delay process affects the information flow. Okay? So alpha is more or less associated then with seasonality. Okay, I can use that parameter to infer about what is the seasonality, if there is seasonality, right? And beta is associated then with the information flow specifically, usually how long it takes for cases to be reported, inserted into the database. Okay? Now, the details are on this paper. I will not go into the fine details behind it. There is also a R package that we developed that implements this model, right? And I will show you the page. And then on the last class, I will try to run some examples of that. And now, just to show one initial example of this application. So we have here an example, right, for, again, dengue cases, dengue suspect cases, actually, for the year 2012. So by the end of the week that is represented that by that small crossed ball over there, so the red dashed curve is the information that we had. So data aggregated by symptom onset, right, with the data that is already in the system, is the red curve. The black curve is what actually happened. So we waited several weeks later and looked back to see what really happened. And the dotted line and the gray shaded area is the estimation that he provided with the information associated with the red line. So it's the model that we ran by the end of that particular week. And for that particular time, we had it pretty well, right? So what came out of this model was able to provide a good picture, a good estimation to what was really going on. Of course, it didn't match exactly, but we shouldn't expect for it to match it exactly, right? Because we're talking about a statistical model to try to estimate what is really going on. Yes?
What should be the curve which are matching each other? Would it be like the dotted line and the red line?
No, the red line is with partial information. So an information that I had at time, which we know to be incomplete. The black line is what really happened. So the black line is what I want to estimate. Okay, the solid black line. So what we want is that the dotted line and the gray area includes the solid black line. Okay, and if possible, to have the dotted lines, which is the mean of the trajectories that we estimate. So it would be my point estimate. We wanted that information to be as close as possible to the solid black line.
So the solid black line is looking back if you had all the information available.
Yeah.
The red line is if you were running the same model with the information you had at the time.
So no, almost it's close to so yes, the black line you're correct. So what is really happened? So it's once we waited long enough, we look back and say, well, what happened at that time is the black solid line. The red one is the information that I had at that time in the database. Okay. So it's the partial information that we used to run the model. Okay. So knowing the red line, we were able to more or less estimate what was really going on, which is the black line. Okay? It's clear? Any other questions? Yeah. Oh yeah, that is probability distribution. Yeah. This is why we have the shade area. Yeah, we shade area. For that example is the 90% credibility interval, if I'm not wrong. I'm not sure if it's the 90 or 95 right now. Not sure, but it's one of those. Now, going back to the other example that we discussed in the beginning for Saudi between 2020 and 2021, now we have here on the right-hand side, again, the same exercise. Each of those colored lines and shades is the estimate that we ran with the information associated with the colored dotted lines. Okay, so by the end of week 16, 20, 24, 28, and so on and so forth, this shows the estimation that we provided against what really happened. Here by the end, remember, this is already partial information by the end here, because the solid black line is the data that we had by the end of week 33, 2021. Okay, so the final block here, the final weeks, is already partial information. Okay? But before that, we can assume that is what really happened, and we can see that, again, usually we get the situation quite well. Of course, we have some errors. Sometimes we miss not only the volume, but also the trend, but usually we get it right. And even when, and there is also another important process here. Look at by the weeks 48, 52, and 3, for instance. This is end of the year. This is vacation time. We have Christmas Eve, and we have New Year's Eve. This has a huge impact in the people that are providing the information, inserting the information into the database. Not only that, also in terms of people that are working in the hospitals filling out the notification sheets. So all the information flow is extremely affected by the end of the year, okay? And so, remember, we run the model, every week we calibrate the model again. But of course, whenever we have a huge shift in the delay process, the model will take some time, some weeks, to take that into account in the parameters, right? Because it will be dominated by the previous weeks, where we had one particular shape of the distribution, of the delay distribution. So if we have a huge shift, the model will take some time to actually incorporate that shift. And so by the end of the year, it wasn't able to accommodate for that fact. It took some time to actually be able to incorporate the new reality, let's say, in terms of the delay process, okay? We are still trying to figure out how to deal with that. We still don't have a solution for that, okay? But yes, sure. That's a very, 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 very good question. And the answer is no. We only look at partial information. We don't go two-way back in time. We define a window, a training window, that also might vary depending on the location, all right? So we take, let's say, a training window of 20 weeks, 25 weeks, 30 weeks, more or less. So close to half a year or less than that. Okay, sometimes you only take like four months. So about no, let's see. Depending on the state, we can use just 3 months, and we already will have a good estimation. Because what is the problem? If we take a window that is too big, the back history will have a greater impact in my estimator. And the situation right now might be completely different. Okay, so this is why we not only update every week, but we also use a moving window of training that is somewhat close to what's going on right now. All right? That's a very important question. Now, so now I'm going to show. So this idea. So I'm showing here application in both SARI cases, dengue notification as well, and the disease itself is not the important part here. I can adapt this system and actually implement this system to whatever the disease, as long as I have in my metadata date of onset or date of event and data of database insertion or upload, I'm good to go, at least in principle. Okay? Of course, if data usually takes too long to be inserted, it might not work that well. Okay? Because it depends. But the fundamental point is much more the information flow than the actual disease itself. Okay? Shoot. Yeah, that's a good question. So here, by looking at the already consolidated data, we might say that, well, we have probably Carnival at that time had a good impact, although the Carnival of 2021 was not that big because we already had several restrictions being imposed but not necessarily followed, two completely different things, right? But yeah, it's something that for sure had an impact, and the celebrations of the end of the year also may have an important effect. But at least as starting this reemergence of cases, because again, a lot of people travel, so the epidemiological situation of one state is more or less seeding other areas due to this process of people traveling from one place to another, right? To visit family, to celebrate, or whatever. So yeah, both things are likely to have had an impact, okay? Especially, particularly here. So now, let's see now how can we then use the things that we discussed yesterday, 2 days ago, and this particular approach of nowcasting, and to see what we can actually do and how this can actually be used to inform action and planning, okay? Starting again with the respiratory infections. So on the left-hand side here, so this is again SARI data in Brazil. And so the horizontal green dashed line, blue one, and the red one are associated with those thresholds that we discussed in the previous class. Okay, so the green horizontal line there is the pre-epidemic threshold that we discussed using the MEM method that we went over, right? So whenever the number of cases is above that line in any week, we are assuming that, well, once it crosses that barrier, I expect cases to go up, okay? Now, we can see then that, well, for that particular year, which was 2018, by at week 18, we crossed that barrier, okay? So we expect that, well, from week 18 onward, we expect it to keep going up. Before that, we assumed that it was just, we could not separate well fluctuations from actual cases increase. But of course, by looking at that, you might say that, well, in fact, by week 15, I could already say that things were starting to go sideways. Okay, but again, as we discussed in the previous class, to be precise, have the exact time when it happened is extremely difficult, right? So we don't expect to actually have that. Okay, we know that we are likely to miss. Again, why? Because otherwise we will have a great chance of triggering false alarms every once in a while. And this is an important aspect that I didn't discuss on the previous class, but which is related. We discussed in terms of sensitivity and specificity, but also another important aspect that is directly associated with that is the confidence that people have in your result. If I propose a model to define thresholds that triggers false alarm too much, people will say, well, this system doesn't work. So credibility is extremely important. And to miss too much in terms of false alarm is an extremely red flag, because you trigger action and you are wasting action, okay? And if you are wasting action, you are also wasting people engagement in whatever your warning is, okay? So at the end, it's best to be a little bit lenient and allow to miss a little bit, but on the other hand, to be more accurate that when you actually do trigger an alarm, is because things are really going sideways, okay? Now, then the high activity threshold and the very high activity threshold is the same idea of, well, I build the distribution of cases that I observe at every week in my epidemic years, and then I look at different quantiles of that distribution, okay, to trigger, well, and that was used to classify the season itself, whether the season was a regular season or if it was too high or extremely high, right? And how we look at that? We look at, well, if the high activity threshold was crossed or the very high activity threshold was crossed, okay? Now, and then the colored background is what we discussed about the endemic channels, right? Which is, again, more or less the same logic, but now instead of separating my weeks in terms of pre-epidemic, epidemic, and post-epidemics, or whatnot, I'm aggregating, I'm constructing case distributions for each particular week. So I have seasons 2011, 12, 13, 14, 15, 16, 17 that were used to train that model. And then, so I have 1, 2, 3, 4, 5, 6, 7, 8 observations for each particular week, right? So for week 9, I have what happened in year 2011, 12, 13, parada, parada, parada. So I build the distribution of observations for week 9, and with that distribution, I can then estimate what is the 10 percentile, 50 percentile, and 90. Why? Because my percentile 10, or my quantile 10, will tell me that, well, cases below that level are significantly below what is expected, right? Because it's below the 10% of the distribution of expected cases for a given week. And this is the green shaded area there. And you can see that, of course, by the mid of the year, the volume necessary to cross that barrier is higher. Why? Because it's the typical time of year where the number of cases are higher. So to be above the expected 10% of the distribution, I have to observe much more cases than in the beginning of the year that usually we are at baseline, okay? Now, the yellow area there is separated by the line associated with the 10th quantile and the 50, so the median, okay? So the yellow line is between low and expected. The orange is between the median and quantile 90. Okay? So is between expected and high. Above Q90, it's the same idea as the green area, but now significantly above what I expect for any given week. Okay? Is that clear? This is the idea behind endemic channel. How we go about constructing the endemic channel, again, I can propose different methods to estimate the quantiles or the deviation from the median associated with the distribution of cases of each given week. Okay? Is that clear? Good. Now, of course, this was before 2020, so this is completely out of the table because it was for SARI as a whole. Well, COVID came and threw all of this out of the window because the volume was completely different, way, way, way above those patterns. Okay? But still, by having that, we were able to identify when COVID-19 cases started to have an impact in hospitalizations. even before we had lab testing in Brazil. So by week 12, March, was the week that the government said, well, from now on, every SARI case must be tested for SARS-CoV-2. At that same week, the alarm was triggered, that the epidemic threshold was crossed. And so we see, well, something's going on here. And we look at the age distribution of the cases that were coming up, and we say, well, the age distribution that we are seeing is not what we expected if this increase was associated with influenza or syncytial virus or any of the usual suspect. So we had two pieces of information there. Volume above expected, and the distribution of cases, the profile, the epidemiological profile of the cases, also different. This is already something that allows you to say that, well, something different is going on. And the only thing that we knew that was different at the time was the introduction of COVID in Brazil, of SARS-CoV-2, okay? So what I want to say is that this type of construction is also useful to try to assess if you have a syndromic surveillance, so based only on symptoms, and you have your historical pattern, your historical epidemiological profile of the pathogens usually associated to that particular syndrome that you are evaluating, you can use that to identify when a new pathogen is emerging. How? By looking, whenever your pattern is different, what is the epidemiological profile associated with the cases that are leading to that change in the trend or in the volume of cases. Okay? So now, by looking at the endemic channel, if we have seasonality, and of course, the endemic channel is only meaningful if we do have a seasonal profile, or if we have a disease that is endemic, which stays more or less in a stable state. Why? Because if the disease, if the period of the season where you have increased volume changes too much from one season to the other, your distribution of expected cases for each week goes to space, right? So this is only meaningful if you have a more or less stable pattern from one season to another. Okay, so but what we get is that, well, once we are able to calculate those endemic channels, we are looking at the seasonal profile itself. This is exactly what we are looking at, the seasonal profile. Why? Because if we look at when is the period of time where those regions increases, this is the period of the year where we expect the most of the cases to occur, right? And we can see it by aggregating the cases by region here in Brazil. This is not the geopolitical division of the country. This is an aggregation that was proposed based on the epidemic curves of each particular state. And what we see is that, well, first of all, in the extended south region, which is region number 4 over there, which is the 3 states of the south plus São Paulo and Minas Gerais, we have a really nice textbook epidemic curve, right? The pattern is beautiful, very smooth curves, very well behaved, really nice. This what says, well, not only we know that cases are usually concentrated in the winter, which is expected because those are the states that get colder in the winter here in Brazil. But now, when we look at the coastal area of Brazil, including Rio de Janeiro and Espírito Santo, or the northern area of the country, what we see is that, well, first of all, the volume is much lower, the pattern is extremely noisy. So what we are seeing is that, well, the pattern is not that clear. It's not always that we have an outbreak, but when we do, in the northern area, usually we expect it to be earlier than here in the south, because you can see that we have a concentration of higher cases around more or less week 17, right there in the north, while here in the south is around week 25, right? The same goes for the coastal area, but it's not that much clear. You can see that it moves a little bit to the right as well. But you might say that, well, when things get worse, usually it's also a little bit earlier than in the south. It's more or less in between the northern area and the southern area. And in the central region of the country, we have something that is a curve that is broader, right? And why? Because that area over there, it gets influenced both by the southern area and the northern one. So whenever we have an outbreak that starts in the north, usually the central area also is peaked in the beginning of the year. When things are more or less fine, seasons that are more or less okay in the north, then it follows more or less the pattern of the south. So the peak moves to the right. And of course, since we are aggregating over all the seasons, we see the mixture of those two patterns. Okay? It's not that the epidemic curve is broad every season. It's just that the peak moves from season to season, from the left to the right, depending on when, on where things are worse in any given season. Okay? This is associated with what I was saying about having or not having a clear seasonal pattern and how it affects your endemic channel if you don't have a clear pattern of when things get worse. Okay? So, and this is why the moving epidemic, this is an adaptation of the endemic channel provided by the moving epidemics method, because as I mentioned in the previous class, the way that the MEM method calculate endemic channels is by first putting all seasons in line. So moving them in time so that the beginning of the upward trend happens at the same time. So it moves, it shifts each season so that they're all one on top of the other. Okay, so for the central area, you wouldn't have this broader period of time, you have a smaller one, but then you would lose when it happens. You will have the profile of how it behaves once the epidemic outbursts start, but when it usually happens will be lost. Okay? There's a trade-off there that you have to check what is of most importance for your particular application. Now, remember that we also discussed that for SARI in particular, for this syndromic surveillance, age stratification is extremely important, right? Why? Because the pathogens that are associated with this syndromic surveillance, so influenza, SARS-CoV-2, RSV, the severity of the cases associated with each of those viruses depends on age, right? So RSV is worse for very young children, influenza, kids, and the elderly, and moving a little bit further into pre-adolescents. SARS-CoV-2, again, the extremes, being far worse on the elderly, but also very young kids are also at high risk, okay? Especially now that and in countries such as Brazil, where unfortunately the vaccination of very young children is way, way below what we needed. So this is also an important aspect in terms of risk age stratification, age stratification of risk. But anyway, so so we can see that the profile that we have, so what the epidemiological scenario in terms of SARI cases for different age strata depends on what are the viruses that are currently circulating. And they can have a different pattern. So looking at aggregated data over all ages, we might miss what's going on in terms both of pathogen and age distribution of the cases. And this might be particularly relevant, especially for hospitalized cases, because we have usually separate areas for pediatric care, elderly care, and the rest of the population, right? So to have an increase in the number of cases in the pediatric population triggers a different kind of preparation in terms of hospitals than, than if it was on the elderly or on other ages. So it's important to know what is going on in this level of stratification, okay? And also, and again, so those patterns are for SARI in general. So since we are facing right now, and this is already a spoiler of this week bulletin, because the data here is all the way to week 18, which was last week. So this is data that is that will become public by the end of this afternoon. And you can see that, well, we see that RSV, which is the light blue line there, it's still it's circulating with extreme importance. The green line, which is influenza A, is also present there and with an upward trend. And COVID, which is so SARS-CoV-2, which is the golden line, fortunately, is still more or less silent. And so one request that we got was that, well, how long do we expect for the current scenario of RSV to continue? How long do we expect for the current situation of influenza A to continue? This is the quality of those estimations. We must be extremely careful on how do we interpret that. Because the farther away in time we are making our projection, the less credible it is. Okay, so we must be extremely careful and skeptical about projection, especially for mid and long-term projections. Short-range projections, 1 week, 2 weeks, might be fine. But as we move further ahead, we must be cautious. So this type of analysis, so what we did was to build the endemic channels, again, because the endemic channels is a way to look at what is the expected pattern, okay? But we have to remember that to be expected is not the same thing to be what really happens. This is the key aspect, right? So you have to take it with a grain of salt. But for internal discussion and evaluation, it is at least useful, right, for planning. But to go public on that, how you inform the population about the fine details and limitations of that type of analysis might be so difficult that it's not worth making it public. Because then you have to, again, deal with information process, credibility, and loss of credibility. So public health communication is a complete different area of expertise that must be taken into account when you decide what is internal information for decision making and what is public information for the general audience and how you deal and process that information, okay? It's not to say that we are trying to hide information to the public, but rather deciding on what is actually informative to the public, okay? So what we did was then, well, we analyzed influenza A, and influenza A, we took as our training window data from 2014 to 2019. Why? Because 2020, 21, 22, and 23, the pattern of influenza A was completely out of character, completely out. So we discarded those years, those seasons, because otherwise it will mess up with our expected pattern of influenza A. So we are assuming that this year, finally, influenza A is closer to what we had in terms of seasonal pattern before the pandemic. Why? Because last year, it was starting already to move in that direction, okay? But 2022, for instance, had nothing to do with what we expect, okay? So this is something that you have to, again, look at your data and decide what seasons you keep or drop out of your analysis. The same thing goes for RSV, but it's slightly different. For RSV, we are using 2019, 22, and 23. Why? Because RSV did not suffer that much with the pandemic. 2020 and 2021, yes. 22 and 23, it's already more similar. And so, but if you have study data all the way back to 2009, why you're just using 2019 and not all the way back? Because of how lab testing was ran in the country before that. We had just a few states that actually ran RSV testing on SARI cases on a regular basis. And since our analysis here is for the whole country, the volume would be completely different because we would have data only for just a few states instead of the whole country. Okay? So again, how do we know that? Because we had contact with the, we dived into the protocols and the actual process of this surveillance system, how it was actually ran at each year. Unfortunately, part of those information are not written anywhere. We only had access because we had access to the actual teams that are involved with this surveillance. This is a huge problem, right? To actually have historical description of the fine details of your surveillance system is extremely important to actually, for other individuals to be able to take that data and provide meaningful analysis for your decision process. Okay, without that, we might have used all the data that was already there, and I said, well, before 2019, there were several states that didn't have RSV at all, so we don't have to worry with them. No, that's not true. They did not have because they weren't testing. And if you don't test, of course, you won't have anything. Simple as that. Okay? But what is important here? So, first of all, this is just total number of cases. It's not incidence. Okay? So it's not divided by the population. And you can see that even though RSV is pretty much restricted to very young children, we see some hospitalizations in the elderly, and then the lethality is way higher. But in terms of total volume of hospitalizations, there's no comparison at all. Young children lead by far, even if you calculate incidence by age. But so RSV is restricted to just pretty much young children, let's say. Influenza A, you have young children, you have elderly, you have adults, adolescents, and so on and so forth. But look at our worst case scenario for the south, the center east. You can see it, or the southeast as well. We have more than 750, above 750 new weekly cases for the south in terms of RSV. And for influenza A, there are about of 150. Okay? So volume is different. And also, the time of year is also different. It's slightly different. Right? You can see on the right-hand side that RSV in the south, the peak is closer to week 20, more or less. For influenza, 24, 1 month later, more or less. Right? Usually. And the same pattern we see for the other regions as well. So we aggregated the data here by the states that are part of the South region, Southeast, Center East, North, and Northeast. And so we see again the pattern is different for each region and is different for different pathogen, both in terms of volume and also in terms of seasonality itself. Now, finally, we can see what other information we can extract for here. That in terms of influenza A, so the black dotted, the black dots here is what we are seeing right now. So it's number of weekly SARI cases with a positive test for influenza A at each week and each region up to week 14. Okay, why 14? We ran this by the end of week 17, and since we are looking at data already stratified by lab result, after week 14, we have what we already discussed about missing information, right? Because either the test was not performed already, the case itself might not have been uploaded into the database yet, the result might have already been processed but not updated into the database, so on and so forth. So we restrict the lab, the positive cases, only up to week 14, even though our data goes all the way to week 17. Okay? And what we see is that, well, for influenza A, let's look again to the south region. Well, what can we see there? What conclusions you might extract by looking at that graph? So the bottom left corner here, which is the comparison between what is going on in terms of influenza A positive SARI cases and the endemic channel associated with those cases. Sorry? The dotted line, the dots is what are actually going on. The lines are my projections. It's earlier, right? So the outbreak in the south is occurring earlier this year than what I expected based on pre-pandemic analysis. Okay? Now, but we can also see that, well, even though it's earlier, it more or less resembles the speed of those curves, right? What divides the golden area and the light red area, right? It's similar. So we might say that, well, if it actually So what we might conclude is that, well, even though it's happening earlier, how it's developing itself is somewhat similar to what we expected. Okay? And if this property maintains itself, we might assume that, well, in terms of duration of the high volume period, it should be more or less the same that we had before. So with that, we can then say that, well, we expect that since it's more or less, it's happening more or less 4 to, I think it was 4 weeks, more or less, earlier. Now we just look, well, we might shift that and think, well, it might reach its peak in about 3 to 4 weeks, more or less. And the full duration of this high activity period still might go over 8 weeks, more or less. Okay, why? Because we are comparing what we expected with what we have and assuming that the time evolution will be more or less the same, even though we can see that it's starting earlier. So we aren't going to say that, well, we have to wait until week 24 to 30 to reach the peak. No. It already started earlier, and it's following more or less the same profile. So it started earlier, and it will end earlier as well, and more or less with the same time shift. So if it started more or less 4 weeks earlier, we expect for it to end more or less 4 weeks earlier, assuming that the profile will maintain the same. Okay? This is an assumption. It might be wrong, but it's what we can offer at the moment. Okay? Sure. So, the outburst already started. So I must do something. But this we already knew. Now, we know that, well, since we have this much longer, what we have, one of the things that we could do is, well, run an assessment of what is the current situation in each state in terms of their hospital beds availability. Because I'm also looking here, looking at the duration specifically, I have an information of, well, how much longer hospitals will be pressured by this particular disease. Okay? And in terms of, and also we see that also that it's already clearly above the median, which is the solid black line there. So in terms of volume, I expect that it will be more than what I was expecting, right? And in the center east, for instance, which is second row on the left, we see that, well, in terms of the time of the outbreak is within at least what between the expected and the mid to worst case scenario, right? Because it's right above the line that divides the golden area to the light red area. So it's not that far away for what I expected in terms of when it is happening. Okay? But also we see that, well, it's already, the volume itself is on our mid to high, between high and extremely high volume. But in terms of duration, well, if it follows that pattern, it's exactly what I expected. Okay? I don't need to run any time shift on my analysis, because already more or less within the expected pattern. And for the southeast, more or less the same thing that we have in the south, for the southeast and for the northeast area. even though it's not that much clear. We can see that on the Northeast, which is second column, first row, the data is quite noisy there. And this is due to the fact that there is a lot of heterogeneity within the states that that are within the Northeast region. Finally, for RSV, we see that as Southeast and Center-East aside is pretty much within what we expect, right? With the data from the previous year. Is pretty much well aligned with the median even. So we can see that for the South and for the South, North, and Northeast, there's still several weeks of high activity to be expected. We are still in the early phase of our RSV activity in those areas, right? Because it's still quite far from the expected peak. But in terms of Southeast and Center-East, we might say that, well, between 1 to 2 weeks more or less, I should start to see it reaching the peak. So a stop in this upward process, and then later on, already to start to decrease, right? Because it's more or less aligned with what we expected, although for the Center-East, it started a little bit lower, and it's already at the red region there, but the profile is more or less the same. The Southeast, more or less the same thing. So higher activity, but within the expected time frame, and it's already, we might say that it's already getting closer to reaching its peak. Okay? Is it clear? Okay, so this is some examples of what we can do with the methods that we have discussed so far. And another important aspect here. So for those analyses, we built the endemic channels in a way that is slightly different, because instead of building the distribution for each week, what we did was to construct a model-based projection. But again, the underlying construction is pretty much the same. We are assuming now that NT is the number of cases at week T. It follows a negative binomial distribution with rate lambda, and lambda then has a parameter beta that is associated with the season. So the rate might change from one year to another, and this is modeled by beta y, okay? So it's a value for each year that will be adjusted with this model, and there is a parameter gamma w, which is associated with each specific week. So we have a parameter associated with the time of the year, and another one associated with the year itself, okay? So roughly, the gamma parameter will take into account the seasonality, and the beta parameter will take into account volume difference from one year to another. Okay, this is the idea. So, and I promise that I will end soon. This is the nowcast provided for the country up to last week. So this is right now. And you can see, so we have on the up-hand panel the nowcasting estimates, which is the, and also a rolling average over. So remember, the nowcasting, it's providing a set of trajectories, right? And over those this set of trajectories, I'm calculating the median for each week over those trajectories, which will be my point estimate, and the uncertainty associated, which is the gray shaded area there. And you can see that there is there is a dark gray area and a light gray area. What is the difference there? The dark gray area is the quartiles. So what it means is that 50% of my trajectories are within the dark gray area. So this is the area surrounding my median, and the light gray area is the 90th percentile. So 90% of my trajectories are within the light shaded area, and 50% of my trajectories are within the dark gray area. So why this is meaningful? Because it not only gives me the range, but how this range is distributed, how the trajectories are distributed along this range, okay? And the blue columns is the current information, what have been reported so far, okay? To have a comparison of what is the data right now and what I'm estimating to be the actual situation. And since we have a set of trajectories here by my model, provided by my nowcasting model, I can take those trajectories and run a basic linear model to estimate what is the likelihood that those trajectories are going up or going down. Right? So I fit a linear model over my set of trajectories and look at the distribution of the slope associated with those linear models. Okay? Now, if I have 1,000 trajectories, I have 1,000 linear curves associated with each of those trajectories. So I have 1,000 slopes, and I can look from this distribution of 1,000 slopes, what is the probability that the slope is positive or negative? If the probability of being positive is above 95%, this is an extremely an extreme indication that, yes, things are going up. If it's above 75%, but below 95%, I say, well, it's very likely that it's going up, but I have not so much as of a strong indication. So I have a strong indication of upward trend and mid indication or moderate indication of going up. And I can do the same thing for a negative slope. If the probability of the slope being negative is above 95%, I say that it is extremely likely that things are going well. The cases are going down. If it's below 95 but above 75, I say that there is a moderate indication that the cases are going down. If neither of those things are true, what I can say that, well, things are more or less stable. They are just fluctuation around the mean. This is what we show here. Okay, so the points here indicate whether for this particular week, what is the current situation in terms of probability of going up, very likely, moderately likely, going down, same thing, and in the middle here, more or less stable. And why do we have two curves here? Because we run the linear fit with different time frames. So we have a long-range analysis, which means that we are taking into account the last 6 weeks into our analysis. And the short-range one is looking at the previous 3 weeks. Okay? So if I take, so you can look here and say, well, if I take into account 6 weeks, things are clearly going up. Now, but if I only look at the last 3, I see more or less a flat curve there. This is why, for the long range, we have here that our projection, that our estimate is that currently things are going up based on the long range projection, but on the short range projection, we see that, well, things might be started to get better. Okay? Again, there are differences in ages, so we can run the same model for different age stratification. And what we see is that, well, for the whole population, things are starting to get better, but actually, this is the current scenario only for the young children. For the rest of the population, especially young adults and the elderly, we are still seeing an increase in the number of cases. Okay? We would miss that if we only ran our analysis for the whole population instead of providing age stratification analysis. Okay? Finally, so it is one thing to show that curve for policymakers or public health agents, and it's another thing to have a set of individuals that comes from different backgrounds in their formation and expect them to be able to actually make an informed decision based on that type of information alone. It might be easier for those who have a strong mathematical background, but not all of them do have that level of training. And to expect that anybody should be able to make an easy interpretation of that type of information is not that much of a good idea. Okay? Again, you have to understand that people have different backgrounds. They have different exposure to different aspects. And in the same way that for us it's easy to make assessment on that, it might be extremely difficult for us to communicate that information to others. And to actually make decisions taking into account that epidemiological situation is not the only information relevant for decision-making process. So this is only part of the information necessary for action. So what we do, and it was the idea behind this trend analysis here, upward and downward trend, what we do is that along with those curves, we provide an infographic that is just based on the projected trend, okay? So each state here is colored based on what is the estimated trend as of now, based on the long-term projection and the short-term projection, okay? This is easier to make a decision. It's the exact same information, but presented on a completely different manner and much more actionable than the previous one, okay? So I won't go into the details about what we are doing in terms of arboviruses because it's already 10 minutes to 11. But what I was going to show is that, well, those type of analysis can also be done, and we actually run some of them for arboviruses analysis, but also we can provide those scenarios in terms of what is expected and alarm triggering. For arboviruses, we can also use climate as already an alert level per se. Why? Because if the climate is already favorable for for the mosquito population, this should already trigger an alert. Because, well, you might not be observing dengue cases or chikungunya cases as of yet, but the territory is already favorable for that to happen. So you should start at least taking action to try to have an impact into the mosquito population, acting before cases start to rise, just by knowing that the climate is already favorable for an outbreak. Okay? So this is the first alert level triggered by the InfoDengue platform is exactly that. If the climate is already favorable for the mosquito, already triggers the first alert level. Okay? And then the next steps are based on analysis similar to what we have been discussing so far in terms of epidemic thresholds and so on. Okay? Good. Thank you. That's it then. Let's go for our break. Sorry that I took a lot of time from your lunch break, but thank you for your attention. And on my final class in the weekend, I will go over some codes associated with some of those analyses, just for us to play a little bit with our package that allows us to run some of those analyses. Okay? Thanks.
So we can back to 15, right?
Yeah. So that we don't push all our schedule too much to the right.